Hello everyone, I am Guanwen Chen from Zhanmin University. This work is finished by Zhanmin. Today I'm on behalf of him to present his work in ICUC 11. The title is Effects of Tree Evapotranspiration, Shading, and Aerodynamics on Surface Energy Exchange and Microclimate in 2D scale street canyon models. This presentation has three parts, including the background introduction, experimental setup, and results and discussion. We all know that rapid urbanization has resulted in a significant increase in tall and dense buildings, as well as a growing population size and density. Urban environments are becoming increasingly overheated and poorly ventilated. Mitigation strategies should be made to reduce the urban heat island effect and improve human health. Previous studies have identified several effective strategies, including raising surface albedo, adjusting urban geometry, altering building material, and incorporating green and blue spaces. Urban vegetation has become one of the most popular options for summer cooling. However, high-quality experiments that quantify the impacts of shading and evapotranspiration remain limited. Further studies should be made to improve our understanding. There are several methods used for urban meteorological study, including full-scale experiment, internal experiment, and safety simulation. Full-scale experiments offer the possibility of investigating the urban airflow and thermal structures from real situations. However, it is challenging to perform high-quality parametric observation studies because of uncontrollable urban geometries and heterogeneous surface materials. Furthermore, the measurements are usually limited with regard to spatial and temporal resolutions and are possibly affected by the anthropogenic activities. Internal experiments can easily control urban geometrical parameters, which have been widely conducted to investigate the urban airflow characteristics and pollutant dispersion. However, the journal cycles of urban thermal environments with heat storage and radiation process are hardly realized in internal experiments. The main advantage of CFD simulation is the ability to perform parametric analysis and provide high-resolution computational results. However, the idealized boundary conditions and simplified physical process may cause simulation uncertainties, resulting in compromised numerical accuracy. Therefore, further high-quality experimental data are necessary to validate and improve the numerical simulations. Uh, that's why we need scale-out experiments. It has been verified as a good option to perform parametric experimental study of airflow, thermal structures, and energy flux in urban environments. Not only building parameters can be easily controlled to test the influence of various urban configurations under the same meteorological conditions. Thermodynamic similarity requirements can also be satisfied. Here are some example studies. We also conducted a scale-out experiment in Guangzhou, China, which is located in subtropical climate region. The name of the project we simply refer to so much. What differs this experiment with previous one is that we incorporated trees to investigate their effects on the microclimate. In the meantime, we evaluated the evapotranspiration amounts of a tree by weighting its mass change. It means the latent heat flux is directly measured. In this experiment, we selected four target street canyons, two with trees and two without trees, and we consider two different urban morphologies, aspect ratio 1 and aspect ratio 2. Aspect ratio refers to the ratio of building height to street width. Furthermore, the canyon surface and air temperatures, wind velocity, incoming shortwave and longwave radiation, and humidity were measured in the center plate of both street canyons. Here are the instruments we use in the experiments. We use thermocouples to measure the canyon surface and air temperatures. We apply Zhanmin anemometers to measure the wind velocity components inside and outside the street canyon. We use the hobo to measure the humidity, and net radiometers were employed to measure the incoming and outgoing short-wave and long-wave radiation, and the mass of the tree was monitored by this weighing scale system. Here are some of the example results. By subtracting the temperature of non-vegetative canyons from vegetative ones, we can get the cooling effects of trees. The results of east wall, west wall, and canyon area of aspirational 1 and 2 are shown here. In each subplot, the x-axis is the time of the day, and the y-axis is the height from the ground. From the figures, it can be seen that trees can cool the environment under the tree canopy, including the east wall, west wall, and canyon area, which it is stronger in aspirational 2. The cooling is up to 5 to 2 degrees Celsius for building surface and air. Furthermore, it's interesting to find that the trees can also produce a warming effect above the tree canopy. They are up to 3 to 1.2 degrees Celsius for building surface and air. In this study, we are curious about the reasons for the above canopy warming. We want to ask a question, what are the related factors to the above canopy warming phenomenon? We carry out linear regression analysis based on multiple variables related to water vapor, radiation, and wind speed. After the analysis, we found that the additional water vapor gather over the tree canopy and reduce outwearing long-wave radiation are two important factors of above canopy warming effect. These two factors tells us that the warming may be caused by the additional water vapor, which is emitted by the tree leaves and contains relatively higher energy, and the tree canopy intercept and keep the energy of the solar radiation, causing less radiation to hit the ground. In this experiment, we measured the evapotranspiration amount of trees directly by weighing the mass of trees. And in each tree canyon, there is a realistic tree and an artificial tree of the same size and shape put on two weighing scales. By subtracting their mass change, the tree evapotranspiration can be obtained. Then the mass change of tree is used to calculate the latent heat flux. Lastly, we get the general latent heat flux of tree. In the figure, it can be seen that the maximum value is 70 watt per square meters for aspirational 1 and 110 watt per square meters for aspirational 2. The peak values appear at around 12 o'clock. In the calculation, we found the tree evapotranspiration occurs for aspirational 1 and 2. The difference of two subplots are mainly caused by the total area of a street canyon. Here are the summary of the conclusion. We found that a tree contribute to 5 and 2 degrees Celsius of under canopy cooling for building surface and air, and trees contribute to 3 and 1.2 degrees Celsius of above canopy warming. And the tree latent heat flux were evaluated in our experiment, and such high quality experimental data is very useful for the safety models and UCM's validation. In the future, we will explore the relationship between above canopy warming and more other variables such as solar radiation, weather conditions, and latent heat flux, and we will use the experimental to validate the model simulations. Actually, this is not my work, and I will try my best to answer your questions. And if you want to know more details about the experiment, please contact Mr. Zhanmin Wu. And that's all. Thank you.
Thank you. Any questions? Any questions? Okay, all right, we may have to move to the next one. Thank you. Next, we have Melissa talking about